In the first part of this video, we talked about effective nuclear charge and how it is a way to compare energies and difficulty for taking off electrons for elements that we're talking about that are in the same period. I cannot emphasize to you again, it's an argument made for things in the same period, which is the horizontal row. What we're going to be talking about now is how to compare things that are in the same family or in different horizontal rows. And I guess I wouldn't even need to be in the same family, but usually that's what we see. So there is a concept called electron shielding. And if you think about the word shielding, shielding means that you're blocking something. And that's how the idea of shielding works. So what ends up happening is that the core electrons, which we talked about, push away and block some of the attraction happening from your nucleus. So the way that it works is that the more layers of core electrons you have, the more shielded your element is from its influence of the nucleus. So what ends up happening is that the more layers of electrons you get between your element and your element's valence electron and the nucleus, the less effect that nucleus has. So effectively, the nucleus has less grip or less hold on the valence electrons because it's shielded, and so it's easier to remove them. So what I'd like to show you is this is the PES spectra for chlorine. Hopefully that makes sense. Remember, always find your highest electron value and then go from there. So the highest energy value here, then we go 1s2, 2s2, 2p6, 3s2, and then we're at 3p5 here. So this is chlorine, okay? Now, I'm going to superimpose fluorine on here. If you look, pink is fluorine, blue is chlorine. The energy it takes to remove the valence electrons, so in this case it's going to be the p electrons from chlorine, is less than the electron or the energy it's going to take to remove the electrons from fluorine. And that has to do with the electron shielding. So we are going to take a look at that in terms of its diagram, and I will show you what's going on with that. Okay. So if we compare our elements, fluorine and chlorine, they are both halogens in group 17 of the periodic table. Fluorine has an atomic number of 9 and chlorine has an atomic number of 17. Okay, so keep those in mind as we get going with this. When we talk about those two elements, I'm going to do fluorine first. So fluorine has an electron configuration of helium, 2s2, 2p5. So when we talk about our valence electrons versus our core electrons, we have 2 of them. Valence electrons, we have 7 valence electrons. And when I think about my drawing here, fluorine has 9 protons. It has the 1s shell, which has 2 electrons in it. And then its valence shells here are the 2s and the 2p. 2s has 2 electrons, 2p has 5 electrons in it. Okay, so right here, I'm going to draw a dashed line. That is the differentiation between my core and my valence. So these are core, these are valence electrons. If I want to calculate my effective nuclear charge, we can do that. I would love to. It's good practice. What you do is you take your atomic number, in this case it's 9, take away your core electrons, which are 2, and you get an effective nuclear charge of 7. All right? Hopefully that made sense. Now, moving on to chlorine, its downstairs neighbor. Chlorine's electron configuration is neon in brackets, and then 3s2, 3p5. And so if you compare these two electron configurations, they honestly look pretty darn similar. We have 7 valence electrons. We have, in this case though, for neon, 10 electrons for our core. So that is maybe going to cause us a little bit of a problem, but we'll check it out. I'm going to do the drawing anyways. We've got 17 positives here. I'm just drawing this bigger because I physically don't have the space to write 17. So I'm going to have my 1s shell that's got 2 electrons. 2s shell has 2 electrons. 2p shell has 6 electrons. My 3s shell has 2 electrons, and my 3p shell has 5 electrons. So in this situation, I said that we had 10 core electrons. So if you think about the differentiation here, we've got this dotted line, the difference between core and valence is a little bit farther out. Okay, I'll check my effective nuclear charge. If I check that, I have my atomic number for chlorine, which is 17, minus my core electrons, which in this case is 10, and I get an effective nuclear charge of 7. So if I am talking about elements that are in the same family, these guys all pretty much have the same effective nuclear charge, which is why the effective nuclear charge argument does not work for elements that you're comparing in two different family, or I'm sorry, in the same family. The vertical argument does not work for effective nuclear charge. So the way that we can explain why it's easier to take off an electron from chlorine in the valence than it is to take an electron off from fluorine has to do with what we call shielding. So what happens is in chlorine, there are 3 layers of core electrons that shield the nucleus from the valence electrons. So if I'm a valence electron out here and I have the nucleus pulling in on me, to prevent my electron from getting sucked in super close, I am going to have 3 layers of electrons blocking me. When I talk about a core electron in fluorine, there are only 2 core electrons and 1 shell worth of electrons. So if I'm talking about a valence electron out here in the 2p shell, I do not have as many layers shielding my valence electron from this nucleus. And it's true that this nucleus doesn't have as many protons, but what's more important is these layers of electrons that are missing. These extra layers that show up in chlorine provide extra kind of blocking or shielding from the influence of the nucleus than they do in fluorine. So if I wanted to explain why fluorine's electrons are harder to remove than chlorine, what I'm going to say is that chlorine has more layers of electrons shielding the valence electron from the protons than fluorine. So if I want to write, I guess, a written example, if you want one, I would say it is more difficult to remove electrons from fluorine than chlorine because chlorine has more electron shielding. More shells of electrons block the, let's say, the nucleus from the valence electrons. This additional blocking makes it easier to remove a valence electron from Cl. And then just as an extra insurance policy, I would talk about fluorine. So I would say F only has 2 core electrons, which provides very little shielding compared to Cl. So to kind of cover your butt in AP, the best thing to do is to talk about both things and what's going on. So you answer the question, what they're asking, and then you compare the two. So if we're talking about Y, if I go back let's get out of here. If we are talking about why fluorine is harder to take those valence electrons away, it's because there isn't that shield of electrons that's protecting the valence electron from the influence of the nucleus. However, something that's kind of interesting, if you look way down here, the 1s electrons are way, way, way harder to take away from the chlorine. But you have to remember, in a PES diagram, we pick away the outside electrons first, and then we get closer and closer and closer. So what happens in the case of chlorine is that we have the outside electrons. These would be your 3p electrons. These are your 3s. These are your 2p. 2s, and these are your 1s electrons. By the time we get down to the 1s electrons in the chlorine, and that's all that's left, there are 17 protons and just 2 little electrons that are trying to hold on. And so it's very difficult to take those electrons away because you have all the influence of the nucleus and none of the shielding happening. So hopefully this makes a little bit of sense, and it's going to be really useful when we talk about our periodic trends coming up. Good luck. If you have any questions,